Hi, welcome to video on remote lab. So in this particular video, we will see the demonstration of one of the triple fat timer application, that is Astable multivator. To start, okay, let us click on this button. So this remote lab has got different experiments. So let us go to 555 timer, in which one of the application is a stable multivator. Let us click on this, and it has got 10 different combinations. Let us select a stable one. So this gives the actual circuit that is used in this particular remote lab, where user can able to select any one of the 10 different combinations, and the design equations are given. Uh, the different values of R1, R2, the value of CT is kept constant at zero point 0.1 microfarad, and we have a control for changing the control voltage, that is V reference, so I can able to apply that. So we can able to see two different waveforms. One is the output square wave, and the other one is capacitor charging discharging of this particular tiny capacitor. So let us start conducting the experiment. So before we start conduct, okay, let us also, okay, let me just click on this conduct button, and let me also take the analog discovery front panel, where I can able to see the waveforms. Okay, I need to add a wavegen. So as you can see here, this is the control voltage which is applied through a second signal generator, which is channel 2 here. So since this requires a DC voltage for initial condition, initial operation of a stable multivator, so let me select DC. So as I can able to apply any voltage, so here I'm applying 2.83 volts. This W1 is not used here, so let me not run that. So I'm running only this. So I need to see the waveforms. So before I see the waveforms, okay, let me just conduct this experiment. So now let me go to this scope, which will going to show me one output at channel 2, which is the square wave. I can see I'm already getting some waveform. This is the clear waveform. Now you can see I'm already getting a waveform. So now to understand what is this waveform is, so let me just take out this scope and wavegen side by side and try to understand what is happening in this particular uh, waveforms. So let me just try to see what are the parameters that you can able to see here. Uh, okay, by default, the amplitudes will be zero point 0.5, zero point 0.5. So this has been already changed to 1 volt. So usually this will be zero point 0.5. In such case, okay, this will also be at zero point 0.5. That is default values. So we may have to adjust that to 1 volt per division. That is the Y deflection, and this should also be 1 volt per division. Now we know that from the theory, uh, the capacitor voltage will charge up to the V external voltage, and it will discharge up to uh, V external divided by 2, half of the V external. If you can see here, I can able to actually measure what are the amplitudes of this capacitor maximum, capacitor minimum, and what is the maximum voltage, what is the width, and all those things. So what I do is I will add those parameters. So I want to measure few parameters. The parameters to be measured are, so they are all defined parameters. So let me measure in vertical what is the maximum and minimum value of channel 1, that is the capacitor charging discharging. Let me see in channel 2 what is the maximum output voltage I'm going to get. That's the only thing that is required on by parameter. On horizontal parameter, let me know the frequency, let me know what is the positive duty cycle, let me know what is positive bit, and let me know what is the negative bit. So these are the parameters that I'm interested in knowing it. So now if you can see here, so I have so many parameters to, okay, let me just remove all of them. You can see the voltage what you have is 2.32 volt here. So this is, okay, let me just let me maximize this. See, C2 is 2.32 volt what you have here, and then you can also see what is the value of your minimum voltage. So it is 1.4. This is, you can see C2 minimum is half of this. This is like VTH. This is VTL. VTL is always half of VTH in case of triple fat timer. The maximum voltage is, this is saturation voltage, which is 3.2 in this particular case. And you can see the frequency is 833 hertz. The positive duty cycle is 59%, almost close to 60%. This is a positive bit, and this is the negative bit, that is the off time and the on time. So what we can do is we can do some variations in this particular experiment, which is possible in our remote lab, because I can able to change the voltage of this control voltage. You can certainly observe this is 2.83, same is there here, which is the maximum voltage, and you can see there is a frequency and positive and negative bits. So you can just have a look at this negative bit, because we know that from this expression, the off time is only dependent on R2 and C. It is not depending on this V control voltage. Even though if I change the control voltage, the off time remains the same. That is, we have an off time of 0.488 millisecond. It should remain constant even if I change this. Okay, let me run this. Okay, see now it is 4.88 millisecond. So if I change this control voltage, this negative bit remains constant, whereas positive bit will change. You can see now, of course, once positive bit changes, the duty cycle changes, hence the frequency will also change. If I reduce this amplitude, you can see the positive bit will reduce, frequency will increase. See here, if I reduce this to maybe around 1.9, see now, let me just stop this for clarity in the measurement. Can you see this is remaining constant as 0.48 millisecond? Can you see the positive bit has reduced? Can you see the duty cycle has reduced from earlier more than I think it was around 59. Now it has reduced to 41%. The, sorry, the frequency was somewhere around 899 hertz. Now it has increased to 1.2. You can see the maximum and minimum are exactly half, and this maximum is exactly equal to the voltage that is set by this control voltage. So let me just show you that. So this is the control voltage what I have given, which is 1.94. Can you see same almost 1.93 volt is there? So I can run it. So as I change this voltage, correspondingly, suppose if I increase the voltage, the positive width will increase. If positive width increases, naturally the positive duty cycle also increase. So whatever is the offset voltage, whatever is the control voltage, that will be the maximum capacitor voltage. You can see I can increase the amplitude to almost something like, okay, 3.38 volt. Can you see it's almost there? It is almost close to that. You can see it is half of that. You can see the frequency is the least one. I can stop it and then measure. Why it's not coming is because let me slightly increase this number of cycles. Let me just make sure that I have more clarity. I can see the width has increased to 68%, but still you can see this is 0.48, 0.46, almost the same. Meaning, whenever we change the control voltage, the negative bit is always constant, only the positive bit changes. Even if the positive bit changes, the overall frequency will change. This will also demonstrate the VCO, that is voltage controlled oscillator, meaning if I change the amplitude of this control voltage, the frequency changes. You can see now the frequency is 688 hertz. If I change this, you can see the frequency is also changing. You can see the frequencies keep on increasing if I reduce the control voltage. So because when I reduce the control voltage, capacitor takes very less time to charge and discharge, actually the frequency will going to increase. So now we have seen that this control voltage has got no effect on the negative weight. If at all, if you want to change the negative weight, only possibility here is you have to change the value of R2. So now let us see for a combination of this amplitude of control voltage and a R1, R2 of 1K and 10K with the diode in off condition. I had a width of 0.48 millisecond and pulse width of positive pulse width is 0.27. If I increase the value of R2, sorry, let me, uh, what I'll do is, let me reduce the value of R2. If I reduce the value of R2 from 10K to almost close to 1K, you can see this is almost close to 1K, like 900 ohms. That is option number 3. This is actually the third option. If I select the third option and then conduct, it will actually make the R2 value is equal to almost 1K, and this is also 1K. Actually, now the on time will become on time resistance will become R1 plus R2, which will be 2K. Let me run now. You can see now since the resistance are reduced, the frequency has increased. So what I do is you can see the negative width also has reduced drastically. It was earlier 0.48, now here it has become 0.058. So what I do is let me just change these timings appropriately so that I can able to clearly see the waveforms. This is fine now. You can increase this and they can stop it. Now you can see the frequency is very high because the resistance values are reduced. You can see the width is 48% and I have the on time off time as so and so. And what I can do is, of course, you can still demonstrate that variation of control voltage and then all those stuff. You can certainly do it here. So what I can do is I can just keep on running it. If I increase this amplitude, frequency will reduce. That you can clearly see there. It's around 9 kilohertz. If I increase this, can you see it has reduced to almost 4 kilohertz? This is how it is happening. Of course, we are not using channel 1 because channel 1 is not connected to my circuit at all. Now let us see one more application of this triple five timer, that is Pwm generation. So instead of a DC voltage, if I apply a sine wave of maybe a very less frequency, you can just take a frequency of something like this here. This is a very low frequency. Let me have an offset voltage of almost 2 volt, and this can be around, this is fine here. You can see, you can already see a PWM type of waveform. Now to see this, let me just maximize this and let me have, because the frequency that I've selected for the sine wave is bit low. Since it is 200 hertz, it requires 5 milliseconds. Let me just make sure that I can see at least 2 cycles. Now you can see this is the PWM waveform. So why I'm saying this is PWM waveform is, you can see during the positive half of the whenever the sine wave is increasing, you can, the width is more. When it is during the negative half, the width is least. So this is, suppose if I just take out this, you can see there is a PWM waveform. So to visualize the PWM waveform very clearly, you can able to take out the channel 1, which is not showing you the control voltage, the capacitor charging discharging voltage. Now this is a purely a PWM waveform. And of course, you can able to get this PWM waveform, need not be in this option of PWM. You can just get it anywhere. Of course, you can see you have a PWM option. Even other than PWM also, you can able to get, if you apply a sine wave to control voltage that is using W2, you can certainly get PWM waveform in any of the possible options. So this way, we can able to see the impact of the effect of R1, R2 change. And of course, unfortunately, at this point of time, my diode is not properly connecting now. I cannot see the action of diode switching on, switching off. I need to check out, okay, what the circuit issue there is in my remote lab. So this way we can able to understand the concept of what is it? A stable multivator. So what you have to do now is you have to select a particular combination of R1, R2, have a look at on time, off time. You can theoretically calculate the on time, off times, and you can certainly verify that using the measurements. The measurements can be done using this view button. So view button approximately appropriately measure the max and minimum voltages on vertical and horizontal parameters on C2. You just measure frequency, different widths and duty cycles. You can able to very clearly understand the working of triple five timer as a stable multivator. Thank you.